Hello everyone, welcome to a Fluid Mechanics 2 CFD project. I'm Mohammed Mirza.
My name is Shoaib Ahmed.
And I'm Haider Ijaz.
This report details our computational fluid dynamics analysis of the Potsdam Propeller Test Case or PPTC. Our primary objective was to develop and validate a simulation framework for marine propeller performance, specifically for the use in pleasure craft with applications like catamarans and yachts. For this project, we simulated the thrust characteristics of a 5-blade propeller at a constant rotational speed of 900 rpm. We tested this with across 5 different advanced coefficients or J values ranging from 0.6 to 1.4, which corresponded to inlet velocities between 2.25 and 5.25 meters per second. As you can see, to characterize the performance, we used non-dimensional parameters. The advanced coefficient J relates our forward velocity to our rotational speed. Our success metric was the thrust coefficient KT, which we calculated using the thrust force generated by simulation and compared against established experimental benchmark data.
In order to optimize computational efficiency and balance accuracy with the student account cell limit, we did not simulate the entire propeller. Rather, we used periodic boundary conditions by isolating 1/5 of the geometry, a single blade passage, and then imposing boundary conditions for periodicity of 5. This was a critical decision because we were conducting this in the Ansys Fluent student version, which imposes a strict hard limit of approximately 1 million cells. Moreover, the stationary domain that we added, aside from the rotary domain, since we are using multiple reference frame method to simulate the rotation, the stationary enclosure was a very large size, around 4 to 5 times the diameter for the inlet and outlet, and 3 times the diameter for the size of the far field boundary condition or the outer cylinder wall. The first step in our meshing strategy after importing the geometry was to add a local body sizing function to the rotary domain, since that is the domain where fluid forces and motion has to be resolved most accurately. And after balancing cell count with the smallest mesh size we could with the student limit, we ended up with a final target mesh size of around 1.14 millimeters with a growth rate of 1.2 applied to the rotary domain area. The next step is to describe our geometry conditions sufficiently, since this is an external flow problem. We can consider the geometry consisting of only fluid regions with no voids, and there is no shared topology or multi-zone meshing required. The next step is to set up the periodic boundaries as specified earlier in order to properly resolve the flow as a periodic 5-bladed propeller, even though we only have 1 blade passage. As you can see, the highlighted phases here representing the periodic sides. After that, we go on to update the boundary conditions. Since we have already done the naming selection within the geometry, most of it is done automatically by the software, as the inlet specified as a velocity inlet, the outlet is a pressure outlet, periodic 1 and periodic 2 with their specific periodic boundary conditions, the propeller being a no-slip wall, or those faces being a no-slip wall, and symmetry referring to the outer cylindrical wall, which is actually a pressure far field condition, but some people also keep it as a symmetry condition since it mimics the same effect. The next step was to add sufficient number of boundary layers in order to resolve the turbulent flow and the viscous forces sufficiently. For this one, we chose 15 layers with an appropriate growth rate to sufficiently merge the inflation layer with the surrounding mesh, and a first height was chosen of 0.0001 meters in order to get a y plus that can be resolved using the y epsilon function. This was visible once we generated the volume mesh, as we can see by inserting a clipping plane and presenting the cell layer at the propeller zone and the rotary domain. Near the propeller walls, we have a large number of boundary layers starting from a very small first height and slowly inflating into the surrounding mesh. The volume mesh settings were generated using the default settings. An appropriate maximum cell size was used in order to limit the cell limit under 1.002 million cells, which is just below the student limit. And of course, we used polyhedra meshing since propeller geometry is quite complex. And this was the best one with the best orthogonal quality that we were able to acquire.
So now opening the propeller in the solution cell, we have our inlet defined here and the outlet defined. First of all, we kept the energy as off because the temperature of the liquid is not going to affect our solution in any way. And the physics function used to define this, to solve this, is K epsilon with enhanced wall function. Moving on to the fluid, fluid has been named as water with the density and viscosity defined. And the rotation of the propeller is set to 900 revolutions per minute. It is defined over here. And the velocity of the water has also been set. For now, the velocity of the water is set as a variable because we solved this using a parametric study so that it takes different velocities based on the J value and solves all of them one after the another. The method used to solve this is a coupled scheme with second order for pressure and momentum and first order for turbulence, which is the default method. And upon solving this for 1000, 2000 iterations, these are the residual values that we got. All of our results, it converged around 600 to 900 iterations, but we let it run for 2000. And we got the values of thrust coefficient, which we then measured to the research paper.
Our results plotting was fairly straightforward. By setting up a parameter that would monitor the thrust on the wall faces of the propeller within the Fluent, the console after every convergence would print out the value of thrust on that blade passage, and after multiplying by 5, we would get the thrust we can expect from all 5 blades working together. This was then compared against the experimental results of the Potsdam propeller test case, for which over 20 other universities and companies around the world have done CFD and EFD data. For our analytical comparison purposes, we are comparing with the experimental data. Here, as you can see, we are consistently getting lower thrust values than the expected results of the thrust, comparing to the real life case. And you can see that the K epsilon model has performed slightly better than the K omega, most likely due to our discrepancy within the Y plus and our first layer height being insufficient. This is also mainly due to the limit of the student cell count, since we could not increase the resolution of the sublayers, the viscous sublayers, and the boundary layers further than our current model. However, this is consistently around a 20% damping or dissipation error, so we are able to still use it for simulations to some extent.
We validated our findings against a reference study that we cited in our report that modeled the same propeller. The study achieved errors under 5 to 13%, but they utilized a commercial software with over 2.4 million cells, more than double our capacity and without any periodic or symmetry boundary conditions, and instead resolving the whole propeller with a max Y plus of 5 all across. This confirms that our elevated error rates were primarily due to mesh resolution constraints at the propeller, rather than at a flaw in our setup itself. In conclusion, despite the limitations of the student version, the framework successfully achieved convergence and demonstrated the correct systematic error trends. This establishes that the model is valid for comparative analysis and preliminary design iterations, provided that the appropriate correction factors are applied. Thank you.